Um, so I'm going to talk about attention, and before that, okay, this is mostly at this moment is used for natural language processing, and also I'll talk about transformers. I'm not sure how many of you heard of transformers. It's pretty new. Of course, it's not the cartoon or it's not the electrical engineer transformer. Um, it's it was introduced several years ago, and I think it's a good kind of succession of discussing RNN because before transformers, NLP, of course, NLP just captured the market completely, just not for long ago, when deep learning came back, and then all NLP algorithm now at that time for a couple years ago was using RNN, but now it's again moving to this new stuff transformers. So we'll talk more about that. But before that, I'd like to first talk about word vector. So if you remember last time we talked about some character-based language model. So and the model, so it's as I mentioned, so as the name suggests, it's character-based, right? Character by character, and nowadays it's more and more common move into this word-based model, and of course compared to characters, typically for character we can just use, I don't know, just for even for ASCII only 256 characters is sufficient, right? So we can afford to just use one hot encoding to represent it. Maybe not very efficient, but for kind of word, for example, consider English word, we can easily have 10,000 words and something like that, or maybe 100,000 words. So then in this case, we really want to kind of reduce the dimension. We want to use a kind of still want to use a vector to represent that, but we want to reduce the vector from maybe if we use one hot encoding, then we can start with if it's 100,000 words, then will be 100-dimensional vectors using one hot encoding, because I may have just if I have one hot encoding, basically it will just list everything. It's a long vector, and maybe it's a word here, there's a Sam here, and for this particular word there's a 1 here, everything else will be 0. So for all the possible words here will be the length of the vector will be the number of all the possible words. So we want to compress this into a much shorter vectors. Typically these vectors will be nowadays will be like 1k, like 1,000, a length of 1,000. So, and we will talk about how to do this. So this that actually I will specifically talk about a tightly known as Word2vec. It's pretty popular and famous, and it's actually sometimes referred as a kind of software package that you can use that to train your kind of tokens like this. It doesn't necessarily to be languages, but all the possible words and becomes a vector representation for all the word there. And the idea, the core idea is like this here. So basically, we are thinking about trying to maximize the joint probability of considering that we have a sentence. For example, I have a sentence here. This is a sentence. This itself is a sentence. Then as we scan through the sentence, we have a word model. The word model try to model the probability of surrounding words kind of given the current center word here. For example, I have a basically a cursor and moving left to right here. When I go up to this word here, the word here, so I'm looking at the probability of this surrounding word. For example, my surrounding word, I can use a larger windows or smaller windows. For example, I can look at the surrounding 5 words. So like 2 words or surrounding 4 words, not including itself, like 2 words like before and 2 words ahead. Or I can just look at the surrounding next word here. Like so, then like the probability, the joint probability, will be just the product of the conditional probability of a given word and conditional probability of embedding given word, and multiply them together. And as you move this cursor, then you also, for this whole sentence, what's the probability this sentence will occur or will happen, given your probability models will be just this cursor keep on moving forward, and then like for example, next character, okay, sorry, for the next word, it will move to this word embedding here, and then we'll multiply the probability of this word given embedding and italic given embedding, and continue to move on. So I have this double product here like this, and the point is like we want to model how to model this probability here. So one very simple way to model it, like, will be just using a actually using a kind of inner product of, think of like for the center word. This is pretty messy here. Let me just erase some of this. For example, like I'm looking at this center word here is italic. For this center word here, VC. So now that center word like C here. So I have a vector for it, it's a VC, and for the outside word or the surrounding word, for example, embedding, I have another vector like UC here, UO here, and then like the probability will be kind of like the inner product of like UO and VC, and of course I need to make it like a probability. Therefore, I apply a softmax here. So and what it means is like this is essentially just normalize this into like UO transpose VC. This is an exponential of that, and sum over exponential UX transpose VC, something like that, for all possible X here. And note that this is I'm summing over all possible words. So it's like, for example, if I have 100,000 words, this is a sum of over 100,000. So you can see this is quite computationally intensive, so we'll address this later on. But this is like the classic idea. So and I call this a Word2vec model. So and you can see the Word2vec model is slightly different, but it's like basically based on the same idea. So it's really quiet. Okay, so if you guys have any questions, just interrupt me. It's kind of difficult if you put anything in chat. I may not be able to see it because when I pull yeah. So anyway, so this is a model. So now then next, of course, like what we are trying to do, okay, maybe we step back a little bit. So then what's the embedding vector? So what's the representation here? If I have the model after training, assume that I train it and kind of maximize the probability, this probability here. So in the sense that like by the way, like I'm writing it like a lot of assuming you guys will catch it immediately. This theta here is basically all the parameters, and the parameters in this case are just UO and VC here. So UO and VC here. So and O, of course, is not just for this particular index O, but it's actually for all the words there. For example, for all the possible words of U and all the possible words of for V there. And then of course, maximizing this probability, I can instead like trying to minimize the minus log this probability, because I typically in machine learning people like to minimize more than maximize. So then instead I can consider minimizing this instead. So again, we have basically, this is the cost function for my Word2vec model, that I have the probability, log probability, that I actually more precisely the minus log probability. I try to minimize that, and you see that I'm kind of summing over t is basically index of the sentence or the document from my I have big T, so many words there, and then starting from the first word, and I just iterate till the last word there, and then I look into the surrounding. So with a window size of basically 2m. So for m words before that and the m words after that, I just want to look at the log probability of that wt plus j. So that's j word after t, and then given this this one, given the log probability of this one, given the center word like wt. And here I simplify the notation here, wt plus j, I just call it O here. This cap stands for outside, and then I see it's like wt, I just shorten that to c here. C is like the center word. And as I mentioned, the model here is just assume that it's a softmax of inner product of U, O, and VC. Now, so this softmax, so therefore I can also write it as an exponential UOT VC over. Note that the normalization factor should be normalized over O here. There's a over U, the index of U there, because it's a summing over O, like all the possible word for the outside word here. The possibility of outside word here should be summed to 1. So I have this exponential UX transpose VC. Something like that. Now if I try to just consider one particular word here, let me again I just give an example. Let's say if I have a sentence here, like let's say this is a bad, a silly sentence here, and let's say the center word here is this is, so this is a center word, and then let's say my M here is just 1, so it's like looking at one word and one before and after. So let's say I have let's consider this A here. Let's say O is this is pointing as this A here. Then I have this P O given C, or like P A given is basically exponential of this U A transpose V is over the summation X exponential U X transpose V is, something like that. Now say I want to, of course what I want is I want to minimize the total cost, right? So as I mentioned again, that like I should iterate one word at a time all the way to the end, and each time I look at sum over the log conditional probability of the outside word given the center word. And if I just consider this a PC or PA given is here, or PO given C here, and I try to, if I try to minimize this cost function, then I want to look at the gradient, right? So I want to basically look at the gradient of, if I only consider that term is just minus log P O given C, gradient of that. with respect to by the way, I forgot to mention in terms of notation here, this theta is basically all the parameters here to be optimized. So therefore this theta here is actually this v, for example, if this is all the alphabet here, all the possible words here, then this theta is basically v this, u this, and v is, u is, VA, UA, and V bad, U bad, and so on. So then therefore if I have, if I just consider this particular center word is an A here, or particular center word of C and O, C and outside word O here, and for this one, if I look at the how this affect, how the change of this thing like UO, VO, UC, VC will affect this P. So I just look at the the partial derivative, right? So if I just look at the expression here, or maybe the expression for this guy here, apparently this this one depends on UO and VC. But also note that therefore it depends on the current center word and the current the V of the current center word and the O of the current outside word. But you see that it also depends on all the outside word of U of all the outside words. So so therefore actually if we really want to do a update in the sense for the gradient in a strict manner, we should just consider just for this this part of the loss alone. I should update all the U's here in the in the parameters. So all these U, just for this term, I should update all the U, and in practice, actually, this can be quite expensive, and we will kind of defer this discussion later on. But here, let's only focus on how this change with respect to UO and VC. Apparently, this PO given C will be depends on UO and VC, right? So let's see if I take the partial derivative of minus log, this guy again. If I take the partial derivative of this minus log PO given C with respect to, let's say, VC. So then, first of all, maybe I should just, even before that, let me simplify this expression a bit first. Minus log PO given C should be equal to a minus log exponential UO given UO transpose VC plus log this summation here, right? So then so therefore this should be equal to minus UO transpose VC plus log summation x exponential UX transpose VC. And okay, so now I try to take the partial derivative of this PO given C with respect to VC. So if I take partial derivative with respect to VC, I should just get minus UO here, right? So I should get minus UO here, and I take a partial derivative of this guy. It would be just chain rule, right? First I have 1 over I have logged this whole summation, therefore I should have first 1 over this summation here. Then I take the derivative VC for this thing here. So I again using chain rule, I should have this exponential exponential UX transpose VC, and then UX, right, something like that. wait a sec, I'm missing something. I should have the summation here. Yeah, I should have the summation here. Summation, and I probably should have like a different something like expire here, something like summation. Yes, because I take derivative of after I have one overlog, I take derivative of this guy, right? All the terms here will kind of like depends on VC, so I really have some here, and I just don't want to have like this overloading this symbol like x here in both of this summation, because they are actually different dummy variables. So here I just use xpi for the summation in the dummy variables in this for the summation in the numerator. So so what's interesting for this one is I can rewrite this as like summation xpi. Basically, I pull this xpi inside. I have this product here get inside of that. So I have like exponential. Exponential u xpi transpose vc over summation x exponential ux transpose vc times ux pi here. So what's interesting here is this one, if you look at this here, it's just the same expression, right? So therefore this guy here is really p x pi given c here. So what you can see is like this one is actually something like minus uo plus the expected of like p x pi given c u x pi. And if I try to update that, like for example, like if I want to update VC here, so using steepest descent, then I should have something like VC is equal to VC minus this partial derivative. So epsilon times this this partial derivative here, right? And so partial derivative is this guy here. So therefore, it's like something like plus epsilon u0 minus epsilon summation x pi p x pi given c u x pi. So something I like to comment on is like, if we look at this expression here, it's like quite intuitive. So the update rule, what it's saying is that like if I observe that I have a center word C here and I observe an outer word O here, what I'm going to do is I will make the word vector VC for my center word more like my outside word. So you see that I will just make it add a fraction of UO to my current center word way. So center word VC representation. And at the same time, I'll subtract the expected U amount for the current I mean with the current empirical distribution, I will kind of compute the expected UX for everyone. The expected U, okay, it's hard for me to say. It's kind of mouthful. I'll just subtract the expected U basically from my center vector also. So make it more like what we are observing, and I kind of at the same time make it less like the average of all the U. So that's what was the idea here. And similarly, I can do the same thing for look at like how the update rule is like for UO. So UO, I won't go through that, but you can easily just do the same thing. We'll eventually get something like that. So it's not exactly the same expression. So, but it also like we can interpret that like rather intuitively. So if also like I try to, given what I'm observing here, if I also try to update UO, then I basically will have UO is equal to basically something like minus, maybe I just write it out first, say minus epsilon of the partial derivative, right? That's partial derivative of this guy. And then of course because I minus both of minus, I have a plus here instead. So plus VC 1 minus PO given C. So what you can see is like what we are going to do is like we will make the outside word representation UO here, so more like VC here, more like the center word, but it's scaled by this probability. The probability is the conditional probability of like O given C. So this is like again a very intuitive way. So what it's saying that if I already have this probability O given C is pretty high, then this one is pretty small, right? So I don't need to make UO more like VC anymore. Otherwise, if like PO given C is more than like this one will be big, then I will try to make UO more like VC. And also like one remark I want to make here is like you see like for each of the word here I have actually two word vector representation, right? I have U this and V this and U is and V is and so on. So in practice, of course you can cascade them like to make 2 times the length of these vectors here. But in practice, it's often that people find that it's sufficient just to use the final word embedding as just a U this plus V this and take the average of them. So now back to the slide here. So this, as I mentioned, this is the actual model that for Word2vec. I have, this is by the Mykonov like 2013, and one thing like it tried to tackle is as I mentioned, like if you use the softmax there, if you look at this here for the softmax here, this is expensive to compare because every time you actually summing over all the words there. So it depends how many words, how many tokens you have. I mean, it can be like 10,000, 100,000 or something. So then it used like a similar idea. So again, it trying to model using just a inner product, but instead of doing a kind of like softmax, it'll just do a sigmoid. So therefore, like this one will kind of make it like a probability already. So it ignore all these other vectors. So it just consider the current inner products and it doesn't consider all the others. And you think of this as kind of like the probability, but of course you ignore too many steps. You want to put something back. So what they did is they have this cost function. So you have this theta again. Is just use U0 and VC here, and you want to make this cost take into account also like you want to subtract back some of this not in your surrounding. So wait a sec. Yeah. So remember C is the center word, right? So what we're going to do is for example, we look at a sentence. Okay, this is easy. So always I can find a sentence on my side. For example, I have a sentence here, and this is the center word. Like the word is the center word, and then I have the surrounding word. Again, like my window may be just the size of 3, so include the before one word before and after. So I look at this word like off here. This is the O here. So this kind of the model the probability like U O minus VC, U off multiply the inner product U off and VC, that give me kind of the probability. And then I want to subtract back all the possible words. So in my dictionary I can have many words. So I just arbitrarily kind of sample some words here, and I want to make sure the sample words to have like small probability that kind of like co-occur with this words, this center word here. So more precisely, maybe I'll sample like 2 times or 3 times. I sample a word there. Then I will have like j here is equal to there. Then I will add this log 1 minus sigma u there transpose v words, something like that. And this include into my cost there. And I will include this several times, something like that. And of course you see that like I want to have like 1 minus sigma here is because I want this probability to be small in this case. So in general, if I sample like any other words, this word is not going okay, most of the time it should not be the one appearing into the surrounding, right? So therefore I want this probability to be small. And in practice, like this, we may just sample it like kind of 10 times. Like so, in terms of training, so you have a cost like this. So when you scan through this whole sentence, so you will each time just generate a cost basically having this, and then I sample like 10 times out of the dictionary and have this sum together, and to form this cost function. So is that clear? So I should go again. I should go word by word. Like for example, I go distributed, then I can I will consider the labeling word. Like now the center word is like distributed, and then the outside word will be representations, and I have this term here. Then I sample maybe 3 times like some of this word here, and then I kind of like compute this guy, and then I move on to this, and then I continue that. Then I go through the entire sentence. I can add all them together and become my total cost. And then from this total cost, I can again do gradient descent, and then I can train this UOMVC. Any question?
Dr. Chang,
yes.
Is the end goal of this to predict the next word?
The end goal of this is to create the UOMVC, a model of this, and you can use it for many things. Once you have the word embeddings, so you can, of course, I just use this immediately as a model to predict the next word if you want, because that actually is a word model, right? So you can scan through, for example, like if I have this model, like given all this representation here, then presumably like probably it's not a very good use for that, but I can take these words as a center words, and then I can go through the entire dictionary and I try to find what's the high probability of this co-occurrence. Then I will say the next word will be the one likely to have a like high co-occurrence. So this is a dumb use of this model, but this is just an example. More typical use will be you remember, like if you go through a deep neural network, always you start with a network, right? For example, if I have let's say last time we have RNN there, right? So you need to fit in some representation into the network, right? So you and this is basically the representation. Therefore, you need to first translate whatever you have here into some of this representation. Also, like the representation should have like fixed size, right? So each of the vector, regardless the length of the word there, like should have the same length vector, right? So for example, like I can have this word embedding model with like 1024, like this is a typical size length. Then like for each of the word there will be just become a vector of like length 1024, and then you can then plug into a deep neural network.
And these words are not handwritten. These words are actually like typed words. They are not handwritten words.
Oh, sorry, I cannot hear you.
These words, are they handwritten words or are they typed words? Whatever word you feed into the model, are they handwritten or typed words?
Oh, okay. Yes, this is okay. This is not even this is not image classification and so on. So we are kind of working on this is typically for like natural language processing. So you already have a piece of text, for example, like from Wikipedia. So you don't need to first scan it, like something like that. So
Okay.
yeah. But then like there's lots of interesting application. For example, translation, the most obvious one, right? For example, if I need to translate this into a into Spanish, for example. So if you remember, like last time we talked about RNN, so typically before like people using transformer will be like this sequence to sequence model. So then you will have like an RNN model that like you're basically keep feeding the each word at a time. And of course, by what I mean by feeding the word, I need to first like do this embedding. Like each word will become this word vector, and then the word vector will plug into the RNN model, and then like each time I plug in a new word there, and of course I when I plug in the first word, like for example I plug in continuous there, this RNN shell or like cell or like LSTM cell will just spit out also the hidden variable, right? So I have a hidden state there, and then hidden state with the next word here, for example the back here, will plug into that there, and then I have another hidden state, and then the next word will plug into that, and so on. Then when I finish, I will have like a one final hidden state. Typically, this final hidden state will be considered as a state summarizing the whole sentence, and then this hidden state will be plugged into another NN. The RNN will spit out the translation, basically one word at a time. I don't know Spanish. I don't know how to translate this one. So but then we will spit out the first word in Spanish, and then this word also will spit out the hidden state. Right? This word will then like put it back as input, and then like this, and this, like this to kind of translate the whole sentence. So therefore, like the use of word vector is very important because this is the first step to do the embedding, like to make word into a representation that can be used in the following steps. So any other questions? Oh, okay. I forgot one remark here also. Like this PW, typically, like of course, like this is sample according to the frequency of the dictionary. For example, you consider English language, some words is much more probable. So maybe I will sample a lot of A is this and so on. And I'll sample much less frequent word, or I don't know, I cannot, my English is bad. I don't know what less frequent word. But I also don't want this to be too extreme. So in the sense like I don't want it to always just sample this guy here, like is this A or something like that. So typically what people does is like this will be like the unigram distribution as I mentioned, like this is like UW is just the frequency of all those words, but I will kind of scale this like as 3/4 of the original distribution. So this will kind of like de-emphasize the very frequent word and gives a chance for like this less frequent word will be sampled as well. So and that is any question? So before I continue further, I like to look at another approach for doing Word2vec. It's like an older approach, but it's kind of like people think of this seems like a more obvious approach. The this approach, right, Word2vec is like based on Windows, right? We look at like a whole sentence, and then we look at the center character and look at kind of windows, and then we move along and then look at another window and so on and so forth and get the frequency of words kind of. So it looks like that this is not very efficient, and if we are just counting a co-occurrence, why don't we just count it once and then just store all the statistics, then we can just remove the kind of just can, in a sense, don't need to store lots of tests in a sense. And that's actually is the idea is like kind of is the core idea of a very famous topic before like very important in language processing, but kind of before deep learning is called latent semantic analysis, or sometimes also known as the topic models. So we will kind of like just look into the co-occurrence count. For example, like if I have a simple sentence, again, I guess it's easier for me to use whiteboard. Let's see if I can switch again. Let's see. So, for example, if I consider simple sentence like this is a sentence I kind of copy from. Let me see. There are too many pens. I pick up the wrong pen here. So for example, like maybe I just make up a shorter sentence. Maybe he's nice but not smart. Maybe he's not smart. Just make up an arbitrary sentence. So what I mean is I can make a coherence matrix first. So in the sense I for example, I have like all the possible words here. He is but not smart, like that. He is nice but not smart. Then I can just count the co-occurrence. Maybe I just also use a Windows. I just one word before and after. Then I look at the co-occurrence when he is kind of occurrence like once, I get twice. So I have like he and is a occurrence twice here. Nice and is occurrence once here, and nice and but like once here. Not and but like does not occur together. Not smart like occur once. So I have something like this. Kind of I have a kind of like a symmetric matrix. You see what I and this symmetric matrix kind of like kind of capture all the statistics of the co-occurrence of the sentence. Oops. Okay, still here. And in the sense like if I have lots of document, then I will have a this matrix will be I can use this matrix itself as a representation itself. Of course, I can use it directly. For example, like I can use, for example, this is a symmetric matrix. I can just say he will be have a kind of this is my representation vector, and is have a representation vector like this, and so on. But of course, if you think of the size of this matrix, will be again huge, because this will be the number of word. Basically, each of the dimensions is a number of word there. So the length of the vector again, that won't be any reduction there. But I can do a kind of like simple reduction for that one using like, for example, PCA or like single value decomposition. For example, I can think of this co-occurrence matrix. This usually this known as this co-occurrence matrix. So I can have this co-occurrence matrix that I just call it C here. So the idea is like I can do because okay, this matrix, if I construct like this, will be symmetric. Then I can do eigenvalue decomposition. So it can be diagonalized into the U lambda U transpose. Let's say this is the C here. So then if I look at the vectors here, like U I can think of this, each of this. Let's say C is like n by n is like the number of words there. So I will have like this U, I can write it as like vector U1 up to UN here. This is column vectors here. And I assume this like kind of like diagonal matrix is like sorted. So starting from the largest eigenvalues. So maybe I have sigma 1 up to sigma n there. So immediately you can see that like if I want to have an embedding of just a dimension 20 or like say just 20, so what I can do is I can just take the first like 20 column vectors and I use that as a representation for all the words. So more precisely, I have like U1 up to U20 here. So, and if I have a particular word, let's say I have a nice here, I can have all these words here. He is, or if I blah 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 blah, I have a nice here, and of course that should be like 100,000 words or something like that for English, and so I can have like here somewhere nice here, and then my representation is simply like this one, something like. You see my point? Okay, maybe this is not. What I mean is like maybe I write better. So this is a vector. So but I have the particular row. Let's say lice is correspond to like row 2000. Then I have this vector like the U1 2000 elements. Actually, if I write like that, I probably should write U2001, but anyway, it doesn't matter. And U20, like 2000, something like that. And this will be my representation. Oops, can you see that? Actually, I think you cannot see that. Okay. Yeah. So, of course, if I have this this matrix, first of all, this co-occurrence matrix is symmetric because I'm assuming a symmetric kind of I'm assuming a gathering the statistics in a symmetric way, so my window is kind of symmetric. I can also have the windows is not symmetric. Like for example, if I only care about like what's the word following like the centering word, then my co-occurrence matrix won't be symmetric. But in this case, it doesn't matter. In this case, I won't have I cannot use the eigenvalue decomposition, but I can use the single value decomposition. So I can still like decompose into like U sigma V transpose. Then I can do the same thing again. I sort the single values, and then like I'll just, let's say if I embedding also like takes the first 20, so I take the first 20 U columns, and then take the first 20 V transpose row as my representation. And again in this case, because you see like that will be like two representations also like per word, and you can add them together if you want, like that's probably like another like very common way to do that. So any question here? So I mentioned this because I like to mention like an approach that is it's very it's quite famous like in terms of word embedding. It's called GloVe. So this is like combining the idea of this Windows approach and also like the co-occurrence approach that we mentioned. So for the co-occurrence that just first build the co-occurrence matrix and then do SVD, it has benefit and also have like disadvantage. So it has the benefit that like if you have only the small amount of data, it's very easy to train and like it's quick. But actually, if you are getting huge, then actually it's not so easy to train because like if you consider all the character, all the words there, then you're trying to do like SVD or like single or like eigenvalue decomposition of like a matrix or 10,000 minus, or not 10,000, right? It's sometimes even 100,000 by 100,000. Then it's not quite feasible. And also like for eigenvalue decomposition, like each time you change the console, if you have a new data there, then you need to redo this whole operation of like diagonalization or like eigenvalue decomposition. So, and the more training approach, right, doing steepest descent, that kind of like approach that we do in Windows model is usually is more easy to have like online training because like if you change the data a little bit, you just use this data to update like compute the cost function and then start from those weights and then update the weight anyway. So then have lots of advantage in this sense. So therefore, like this word, like back in 2014, like by Manning Tell, like they basically combine these two ideas. So they have this cost function instead like this. So again, like they have this PIJ is the co-occurrence matrix. Basically, they gather the first gather the statistic of the co-occurrence matrix, and then they have this UV again is the representation there, and if you look at this here, it's just trying to train UV such that it's kind of close to PIJ, right? Or close to log PIJ more precisely. And for this PIJ, FPIJ, you can think of this as just PIJ. So this is kind of scaled. This cost function is scaled by how kind of frequent this co-occurrence occur, like this IJ occur. But like they have this f here, basically this f function is something like this. So they are trying to kind of like make it like when this co-occurrence probability is too high, they just want to clip it off. They just don't want to have like some of these words is too frequently appear together. For example, he is. That's kind of like kind of overload the model basically. So then like they just have this f function to kind of keep off this like effect here. And this is the GloVe model. And now let's look at like some of this usage. Actually, some of you guys asked the question like, what's the use of the word vector? Of course, I mentioned that like one of this is like very important as the first step for the word representation. Basically, for all natural language processing, this is basically the first step. But also like there's some interesting application, and this is illustrated like in terms of like this some of this evaluation tasks. Actually, this slide I really want to talk about evaluation tasks to kind of like evaluate the how good the those word vector is. But at the same time, I just think of this as like application still is very interesting. For example, like one of this is like this word vector analogy. For example, based on the model, you can ask question like man to woman is like king to what, stuff like that. So how you're going to use this word vector is that you basically will you kind of like after you train the word vector, let's say for each of the word vector, I would just call x something. For example, I have x king, like this is a word vector. So what I'm going to do is I try to look for the word to maximize the probability that not probability, the maximize the inner product between like x king plus x man. Oh, wait a sec. Does it make sense? I think I make it wrong. I mean, it should be something like the x woman minus x man. Yeah. more like this inner product with some xi here. So some kind of like maximizing that, but I need to normalize this vector here because in general this vector does not need to be actually this normalization is not important, but anyway. So something like that. So if I try to maximize that and try to find the argument that maximizes that, you'll find that the word kind of word embedding model, Word2vec model, like they will give you queen here basically. So you can see some of this example, like for example, like we have like was if like France to Paris, so like was is to Italy, something like that. That will give you warm, and then like if you want to see like what's bigger, if you consider like you can just read this like so the analogy, for example, sushi to Japan is like Germany to, I don't know how to pronounce it, Belarus, I don't know, and then like copper, CU to copper is like go to AU, stuff like that. And also yeah, maybe I will skip that. This is some other so this is like okay, maybe I'll spend a little, talk a little bit about this anyway. So why we want this is like we want to evaluate how good this word vectors is, right? So there's some, if you really design new word vectors technique, you can test it with some intrinsic tests and also some extrinsic tests. So the extrinsic one is like more like real world one that using, for example, an apparent one if we machine translation. But of course, evaluating the word vector with this kind of task is more expensive, like you need more computations. But if you evaluate with this just word vector analogy, like the example I gave you, it will be kind of easier because people already build data set for that. So you can just test it on a data set like automatically and then can compute the score, like how good or bad like your word vector is. So this is another possible intrinsic test, is like trying to see kind of like the correlation of two words. So I don't have an example here. Oops. So something like they give you two words and then you decide how correlated this are. For example, I have like just this like man and woman. So they ask like lots of people and see like what they think, like how correlated like this word supposed to be, and give a score for that 0 to 10, and then like and try to have the model like fit with this judgment there. And another kind of like this is I guess people also sometimes consider extrinsic task, but it probably is not, shouldn't consider as a downstream task. It's like this long as this name entity recognition. It's just like give you a sentence and you try to identify like the category of that word. So for example here, John lives in Oklahoma and so on, and study at OU. So trying to kind of identify John is as a person, and Oklahoma is a place, a location, and OU is an organization, something like that. Okay, so what I'm doing with time, actually, let me take a look. I have 7 minutes. I'm thinking whether I should go further or like so. Yes, actually, I maybe I just say something like motivation. Then I will start like next time with the actual attention model. So, if you, I guess like maybe it's better like I show another slide that we have. show the slide last time. So if you remember, like some application of RNN, right? Say like we have the figure we draw there earlier, or the whiteboard, that trying to do was machine translation from kind of sequence of words, basically like it's basically like machine translation is like sequence of word to sequence of word, right? So therefore people sometimes look at this sequence to sequence model here. So the problem of this model is that if you think of like when you have a long sentence, for example, like a relative long sentence, I said several lines of sentences, then you are really trying to make the models to memorize lots of stuff before you actually start translating. So therefore, a model like this is typically work quite well for short sentences, but when your sentence get longer and longer, it just the performance got just decay. So that's why like actually a very influential paper, probably I'll talk about it next time, is like a starting point of the attention model. At least many people consider that, or like modern attention model is by Banjo's group. I think it's back 2014. Is that they try to instead of like for the decoder here, trying to wait for the encoder to memorize everything. Okay, sometimes people call this part like encoder and this part decoder. So instead of like let the encoder trying to memorize everything, and then like decoder just look at the last kind of summarized information to extract everything from there. The decoder trying to directly attend to individual words. So basically, you're trying to attend to like all of these incoming words, and with different degree, and the degree of attention will often based on like whether you think it's a match of like what you're currently interested in. So for example, like if I say like I cannot speak Spanish, I say. So maybe no hablo. Oh, my handwriting is very horrible. Español. I guess no puedo. I don't. Hablo español. I'm not quite sure. Probably it's not right. Español, something like that. So when you go along this sentence, when I try to do the translation here, maybe no habla. When I go to like here, maybe habla. So I want to really attend to speak here, something like. So of course my sentence here is pretty short. It does not matter too much. It looks like it's like one-to-one correspondence as well. But if I have like more real sentences, for example, like let's see. I think halase halasemasen. Oh, I cannot. I forgot my Japanese and already. But for example, for Japanese, like the word ordering will be quite a bit different. So you have the word like near the end. So still, you want to train the model such that like maybe even though my order, so even though my order of word is not like one-to-one correspondence, like so nicely, still it knows where to pull the corresponding information. So okay, I guess like more or less time should be